Alright, so we've talked about digital PSG. Let's get a little deeper into the guts of the actual equipment. When the signal occurs on the scalp of a patient, it is amplified, mixed with another electrode like a reference or an exploring electrode from a bipolar derivation, and then it goes into more processing for visual display and storage. In order for the original signal to get to display and storage, it has to travel along meters of wires, and it has to be juiced up to be made bigger and filtered so that we can only see what we want, converted to DC to AC or analog to digital, and whatever else I can't think of right now. That is a lot of processing and changing of the signal. Have you ever played a game of telephone where one person whispers a sentence to another, then that person whispers what they heard to another person, and the cycle repeats itself to the last person who repeats the sentence to everybody else, which is usually something totally different from what we started with? All the different interpretations and limitations of separate yet integrated equipment have a hand in molding the signal, and that leaves a ton of room for error or for the signal to be messed up just a little bit, and that in turn is like a snowball effect and it affects everything else down the line. You may have heard that processed foods are not as good for you like whole foods, like raw potatoes, greens, and vegetables and fruits and stuff like that. The things they do to make food last longer or taste better or give you artificial nutrients is what we call being processed. We really aren't sure how that affects our biome and health, but it's clear that making food at home or eating food from original ingredients is a more healthful option than highly processed foods. Reviewing from the last time, signal sources that come from a person's intrinsic biopotential firing, so straight from the horse's head, so to speak. These are EEG, EOG, EMG, and EKG. Transduced signals are signals that are not electrically produced off the person, but the person does something that we want to know about, like breathing, and a device called a transducer takes that breathing energy, you could call it, and it converts that into an electrical signal that we can actually see. Transduced signals like airflow, or they include airflow, like the thermistor and the nasal pressure, as well as the effort belts. Those signals usually don't have definitive values, as much as they just show an upwards and downwards deflection over time. Ancillary equipment, however, does provide a specific numerical value that needs to be accurate. For this reason, equipment like pulse oximetry, capnography, and CPAP flow generators need to be calibrated. And that's what quantitative or numerical data is more important to calibrate than qualitative, or the upwards or downwards trends of airflow and respiratory effort. And so remember, a transducer is a device that converts one form of energy into another. So because we have tiny electrical signals in the brain, we need something to make that signal big so that we can read it. That's part of what an amplifier does. It has to boost the signal for us to see it as well as strong enough to be able to to be passed and processed through all the other individual processing components. So how does an amplifier take the signal out of the conglomerate of signals that come off the head and make that bigger? Due to the electric nature of components and things, when you pass a signal through a component called a triode, or what we called it a triode a long time ago, that would effectively cancel out the same or like signals that were coming in from two electrodes and pass through just the signal we want, but at the same voltage and current that it was signaling all those signals at. So all that voltage that was going towards that huge signal that was gross, all that voltage is going to passing through just the signal we want. And that can be much bigger. Here's a graphic representation of a simple version amplifier. The input comes into what's called the preamp, and that's what handles most of the signal processing, and then that flows into the main amplifier, which boosts the signal for the output. A buffer is a component similar to like a transformer, but instead of voltage up steps or down steps, it gets a signal ready to go from a high impedance source to a low impedance source. Everything we get from the patient is considered high impedance. And when we put that signal through a highly complex and accurate piece of equipment with very low impedance, like our PSG stuff, it can actually make that signal incredibly unreadable. So a buffer takes the high impedance signal and processes it so that the sensitive equipment can take it and digest it. That sends it to the differential amplifier, which takes out the signal we want from the original native signal, and then it is further boosted with a power amp. All of these stages have the potential to cause distortion if they aren't tuned or calibrated accurately, which is something a standard sleep technologist does not typically do when you're working on patients in the lab. Unless you're a freaking cool person, and I have total respect for you, unless you've had training in such things, and then that's different. If you learn it on your own and you can do it, that's cool. Electrical components nowadays, unfortunately, are manufactured in ways that you can't really fix it, or you're not supposed to fix it on your own. Companies don't want you going in their product and making it better or figuring out how to make it your own. Electronic chips nowadays are manufactured on the order of nanometers, and you can't really fix anything like that with the tools we have. So if the tech is able to do anything themselves, it's usually replacing a module that could be easily taken in and out and replaced. But that's rarely the case now. If you're familiar with John Deere tractors, they're the same way. Used to, the machinery was accessible and you could get in there and fix it yourself. But now the technology is such that you have to have the tractors have a computer like a car, and it has signals and codes that you have to access to actually figure out what's wrong with the tractor. And so the farmer is dependent on John Deere's service, which is incredibly expensive. I think it's like maybe $1,000 just to come out and get a computer code, when they might have just been able to fix it themselves. So distortion introduced at any level amplifies distortion as the signal goes from stage to stage. Distortion is noise in the signal which could come from anywhere, and maintaining signal integrity means the source signal is as unchanged as possible as it passes through amps. Selectivity is the feature of excluding unwanted signals coming through and only amplifying the signals you are wanting. Let's expound upon common mode signal rejection. Common or similar or like signals come in through the original electrodes, and the amplifier cancels out those signals, only leaving the signals that are different between the two electrodes. Here, we would have the exploring electrode represented as G1, the reference electrode as G2, and they both flow through this orange triangle, and that represents the ground wire and the main reference. In the real world, there's no such thing as a perfectly balanced amplifier, and on top of that, the common mode rejection ratio can be different. Amplifiers are rated based on their common mode rejection ratio. The ratio indicates how much voltage is needed to make the same output as the ratio wants. For instance, a common mode rejection ratio of 2,000 to 1 means that out of 2,000 signals, 1 will pass through. It also means that an original signal has to be 2,000 times greater than the frequency we want to be included in the output. So if there's an unwanted signal, that thing has to be 2,000 times bigger than the signal we want to get for it to be in the signal. Generally, I believe PSG signal systems run at about 10,000 to 1. Because we're talking about noise in the signal, we generally think of that as an audio feature. We measure noise with decibels, but that's not generally something we ever think about. There are two components that hold the three stages of amplifiers that we deal with. The preamplifier, which houses a buffer for the signal transformation, and a differential amplifier to compare the two input signals. And then you have the main amplifier, which is a driving power amp that boosts the signal to either power galvanometers for ink pen analog signals or a digital signal for a CRT or HDMI display. That's a lot of old words. HDMI is what we hook our TVs in now. That's generally what you're going to find at the sleep lab. CRT monitor is that big box-looking monitor thing. Those were really dangerous, actually, if you tried to take them apart. Galvanometers were almost like a transducer that takes an electrical signal and turns it into energy that provides motion, so that when the power would come through the galvanometer, it would deflect the pin. That's the mechanism that would make that happen. Remember, the buffer amplifier takes a high impedance signal from the patient and matches that impedance to the relatively low impedance of the rest of the amplifiers. This follows the same principle of wanting two electrodes on the patient to be low and relatively equal value. If one electrode is 5 kiloohms and the other is 15 kiloohms, that difference in impedance is enough to distort the display signal. The buffer does not amplify signals, but it does separate the amplifier stages. Here's a diagram of the signal going into the buffer amplifier, which is usually on the head box or jack box. Whereas we consider the signal from the input from the patient a high impedance signal, it must be processed so that a low impedance cable can transmit the stream as noise and distortion free as possible. The second amplifier in the sequence of is the differential amplifier, which subtracts the reference electrode, or G2, voltage from the exploring electrode voltages, causing a voltage difference in output. In math, difference means subtraction, so a differential amplifier subtracts. Differential amplifiers are how we have referential montages. Those show us just the potentials that come off of the scalp by comparing that signal to a 0.0 electrical baseline reference electrode. Refrode. That's what we should call a reference electrode. A refrode. And an explode. That's funny. Anyways, without that reference and a steady line, the waves could travel further up and down across the screen, and then they'd be unreadable. We just discussed referential montages or derivations. Remember, derivation is a set of two electrodes that make a signal, and a montage is a collection of derivations. A referential derivation or montage is when we have the exploring and reference electrodes, and we just really get the signals coming from the exploring electrode. On the other hand, as it is with a lot of seizure montages, a bipolar montage compares the voltages between two exploring electrodes. Using this kind of montage actually allows us to pinpoint where the seizure focal point is. The spikes literally point to the epicenter. We do technically use bipolar derivations, as the chin and leg EMGs are compared to each other, as the EKG does that as well. We saw this earlier. It's the common mode rejection diagram, and it's actually the same thing as a differential amplifier diagram. Here it is as it relates to the patient's brain and that source signal going to the amp. Here you can estimate the distance between the reference and exploring electrodes. Generally reference the opposite side of the head, because the distance between all those electrodes is more equidistant than if you were to do it from the same side electrode. So let's see. Let's just say this is F4 and O2, and let's say there and there. If we were to gauge, just eyeballing it, there, and there, versus here to here to here, because we've added just a little bit of distance, these are this one's, really closer, then it gets a little closer, and then it travels a long way. This is the same, but adding distance makes those two differences not as bad as this one. So that's why we go from the opposite direction. The distance between electrodes has the potential to make a difference in the amplitude of the waves. guess what? We already know how amplifiers do their sophisticated calculations, and this is where we solidify that knowledge. There are two things we have to keep separate. The first is the reference. We know that the reference is supposed to be a 0.0 non-active site. The Explorer is really all the signal that we're reading, but only get there if we compare it to the reference. And keep in mind that when I say that the reference is a 0.0 non-active site, it's acting as that, because that's what the exploring electrode is also dealing with. It's all the extra stuff that's happening in the brain. But because it's on a bone and not on a brain part, it's relatively non-active. So when I say 0.0, that's not the voltage. That's just it's acting as a baseline. And that reference voltage changes, as you can see here. And that's just how electricity works. The Explorer is really all the signal we're reading, but only if we get there comparing it to the electrode. So the second thing to remember is the difference in polarity, negative or positive. In EEG, electropositive voltages create a downward pin deflection. Thus, a negative signal input is displayed on our screen as an upward deflection. This is one of my favorite tools to visualize the calculation. As long as you keep the exploring and the reference separate and you remember the principles of subtraction, you'll be fine. And by the principles of subtraction, I mean when you minus a minus, it becomes an addition. Or when you subtract from a negative number, you're adding something, adding a positive. We can think of positive signals as being on a mountain. The 0.0 baseline could be the flat beach sand, and the ocean could be negative signals. So let's look at the top example. If the exploring electrode, G1, right there, takes a hike up the mountain, a positive 75 microvolts, and the reference electrode, G2, is just hanging out at base camp around 10 microvolts. The difference of distance between the two, or amplitude in our case, is a positive 65 microvolts. How did we get there? We took 75, positive 75, and subtracted a positive 10. That's kind of easy, and that's 65 positive 65, and that is above the reference. It is positive, so the deflection is downwards. If we then have an explorer checking out a shipwreck at negative 75 microvolts in the ocean, and the reference G2 is floating somewhere below sea level in the command ship at negative 10 microvolts, negative 75 microvolts minus a negative 10 microvolts mean we're adding 10 microvolts. So negative 75 microvolts plus 10 microvolts equals negative 65 microvolt output, which is an upwards deflection. There are a couple different ways you can think about this problem, the mathematical way and this way, the intuitive approach. We can think to ourselves, is the explorer on the mountain or under the ocean? And then, is the explorer higher or lower than the voltage? Which then leads to which way does the pin deflect? And then finally, what's the difference between the explorer and the reference? I kind of have a little trouble with that just because I get positives and negatives mixed up. And so if I just think about it that way, I'm going to screw it up. But some people can keep it straight. So here is, we've got exploring at a positive 75 and references at a positive 10. Is the explorer on the mountain or under the ocean? It's positive, so they're on the mountain. The reference, the explorer is higher than the reference. The pin will deflect, since it's positive, it will deflect downwards. So what's the difference between the explorer and the reference? 75 minus 10 is 65 microvolts. It's always good to be specific. Or you can follow up with what we have been doing the whole time and just plug in the information into the formula G1 minus G2 equals output. All you have to remember is the pin deflection in EEG is opposite. So let's see. Here's the same problem as we kind of explained it mathematically. You kind of have an intuitive approach to it, but really you always have to do math. Here's another example. Let's say our exploring G1 is under the ocean at negative 55 microvolts and the reference is hanging out in a lighthouse at a positive 10 microvolts. G2 minus G1 translates into negative 55 microvolts minus a positive 10 microvolts, which equals negative 65 microvolts. Negative signals are represented with an upwards pin deflection. One more. You'll have to think about future terms with me to make this happen, but we have an exploring electrode at the deep sea base station at a negative 105 microvolts. We can't really do that yet. It's easier to go to space than it is deep sea. Negative 55 microvolts means a negative minus a negative 105 microvolts, which ultimately means we are adding 105 microvolts equals a positive 50 microvolt output. The deflection for a positive signal is downwards. All right, here are the general takeaways from this that are good key concepts for the BRPT, although I won't be surprised if there was a G1 to G2 differential equation on there. We reduce distortion in our signal by having low impedances by scrubbing the skin well so that the impedance is less than 5 kiloohms, but is also relatively equal to the other electrodes. I know a lot of good technicians who are so precise with their scrubbing, they've been doing it forever, that they can get a clear 2.5 kiloohms across the board, making great potential recordings. And impedances are good. But if there are other electrical disruptions or the wires aren't bundled well and they pull when the patient moves, it's going to be noisy. That's just another step in the process where noise can enter. Okay, I hope you find this stuff interesting like I do. This electrical knowledge is applicable to so many different things. I use it when I record music stuff because there are a lot of noisy things that I can get rid of my questionable sound just by using a preamplifier, a power amplifier, and a filter. So the more you understand this stuff, the more you're going to be able to understand and use that for your critical thinking, and that's huge if you can do that as a sleep tech.